Welcome back to the next topic in IB physics. Today we'll be looking at B.3 Gas Laws. So I'd like to say before I begin that this topic is probably the easiest one in both IB physics SL and HL. And by easiest one I mean the easiest one that's weighed heavily in exams. So if you understand this, you'll be quite well set for the exam because it's basically free marks in comparison to many of the others. So let's just begin. So the first concept is pressure. You probably already know about this, but it just means force per unit area. So if I push on the wall with my hands and I apply 5 newtons against the wall, and the area that I'm pushing is 1 meter squared, then I'm applying 5 newtons per 1 meter squared, which is a pressure of 5 pascals, that's the unit, or 5 newtons per meter squared. So that's literally it. Next we'll look at moles. So moles are not this little animal here. Moles just means 6.02 times 10 to the 23 amount of something. And that might sound really weird initially, but it means literally just that, 6.02 times 10 to the 23 something. So if I have 1 mole of footballs, I have 6.02 times 10 to the 23 footballs. If I have 1 mole of salt, I have 6.02 times 10 to the 23 grains of salt. And if I have 1 mole of light switches, then I have 6.02 times 10 to the 23 light switches. So that's literally all that means. But generally we talk about moles as in being atoms or particles or something like that. So if I have 1 mole of helium, then it means I have 6.02 times 10 to the 23 helium molecules. And the symbol for moles is basically just a small n, like this, and the unit is just moles. And there's 2 formulas here. One is number of moles equals m over mr, and a number of moles is just how many moles I have, so how many atoms of something do I have. M is the mass in grams, so be careful. This is the first time we're using m in grams and not kilograms. And mr is the relative atomic mass. So for example, hydrogen has a relative atomic mass of 1, so that's like the number you see on the periodic table that's written. So you just add together all of the things. So for example, if you have NaCl, so sodium chloride, which I think should just be salt, you would just add up the relative atomic mass of sodium with the relative atomic mass of chlorine, and that's your Mr. So yeah, that's pretty much it. And the unit here is basically grams per mole, which gives you moles. Sorry, not grams per mole. This is basically grams here, and relative atomic mass here is measured in grams times moles. So when you divide them, you're left with only moles. And here we have number of moles equals n over Na. So basically n is Avogadro's number, this one right here, and Na is Avogadro's number, so what this is right here, 6.02 times 10 to the 23, and n is specific to that particle. So if they say there's 1,000,000 atoms, then you put n is 1,000,000. If they say there's 100,000, then n is 100,000, and you just divide 100,000 by this number here to get the number of moles. So it's very easy. Now, gas laws. There's 3 types of laws. Charles' law, Gay-Lussac's law, and Boyle's law. I promise it's called Gay-Lussac's law, that's not a joke. But here's the 3 of them. Now here I've replaced Gay-Lussac's law with Avogadro's law because Gay-Lussac's is quite similar, so we'll just look at it. So Boyle's law basically says V here is directly proportional to 1 over P, so V and P are inversely proportional. And then this says V is directly proportional to T, which is Charles's law. And then this one here says that V is directly proportional to N. So as V increases, N increases, or more properly, as N increases, V increases, right? So basically what that means is that Charles and Avogadro's in this here are basically just straight lines, and Boyle's law is like a reciprocal curve between V and P. Something to be careful about though here is that these all have, this one right here has a 1 over p, so they could give you a trick axis or a trick question where they give you a 1 over p as the axis, and then that would mean that you have a straight line because v is directly proportional to 1 over p. There's no need to memorize these individually, you just need to know that they exist, and everything here is combined into this one law, so you can see v and p are inversely proportional, v and n are proportional, and v and t are directly proportional, and this equation is PV equals nRT, where P is pressure, V is volume, N is number of moles, R is the gas constant, and R has a value of 8.31, and T is the temperature in Kelvin. So, yeah, that's pretty much all you need to know here. Now, let's have a look at real and ideal gases. So, real gases are basically gases in real life. They have intermolecular potential energy. They do not obey gas law equations, and they have a non-negligible particle volume. So that that basically means that this gas law right here, called the ideal gas law, doesn't really apply to them. The ideal gases, on the other hand, follow this gas law, so they follow all of these gas law and also Gay-Lussac's law, and so they, in order to make them follow these laws, we have to assume that they have negligible particle volume, don't have intermolecular potential energy, and many other things. Now you might be wondering, what are those many other things? Well, that's what I'll get to here. So we're looking at the kinetic theory of gases. That basically just means it's a way that we can think about how gases work. And to understand how gases work using the PV equals nRT model, we need to make these assumptions. For an exam, I suggest you memorize 3 of them at the very least, because usually questions will ask for 3 if they do ask. Or perhaps 2, but it's just better to memorize 3 to be on the safer side. But here's how the theory works. Basically, a gas has many identical molecules. The volume of the molecules is negligible, and molecules move randomly, which means you can't predict how they move. They move continuously, so they never stop moving, and they move fast, so at very high speeds. All molecules obey Newton's laws of motion, which means that they obey the first law, the second law, and the third law. They collide elastically, meaning that they never lose kinetic energy, so their velocity doesn't really change by colliding. And there's no intermolecular forces, meaning that, like, for example, there's no attraction between any 2 particles, and there's no external forces, meaning we can ignore the stuff like gravity, friction, air resistance, all of that stuff. We can completely ignore it. And why is this important? Well, it kind of explains how a gas exerts pressure, right? So if we go back to the first slide, we think, how would a gas exert pressure? Because it's not really exerting an actual force. I mean, if you touch a gas, you don't feel an actual force. So how does a gas exert pressure? Well, I'll give you a moment to think about it, and then I'll answer it. So just try and think about it for a second, and then I will answer it. So pretty much what a gas does, if we go here, is that the gas is basically moving randomly, continuously, and fast. So every single time it collides with the container wall, it hits elastically, and according to Newton's law, because it now hits and bounces off, there's a change in momentum because the direction changes. And when there's a change in momentum, there's always a force exerted, right? We know that F equals delta P by delta T from topic 8.2. So when it hits, there's a force exerted. And when there's a force exerted on a unit area, that's basically pressure. So that's basically how a gas exerts pressure, and this is what explains that. There's just one final thing that needs to be covered in this topic. It's average kinetic energy and internal energy. So there are 2 new formulas here. U equals 3 over 2 NKBT, where U is internal energy, 3 over 2 is basically a scaling factor. N is from here. Uh, it's the number of particles or atoms or something. It just depends on the question. KB is basically the Boltzmann constant that's given in your data booklet, and T is the temperature in Kelvin. And so basically, what it means is that the internal energy, so the sum of potential and kinetic energy for a real gas, or just the kinetic energy for a ideal gas, is this. Now we also know that U is 3 over 2 nRT. So sometimes if you need to find say big N here, we can cancel off the T's. We'd have this N here, and then R and KB are just constants, so you just rearrange for N. So these two equal each other, and the way that this is derived is by using EK as half mv square and equating that to 3 over 2 kBt, which is the EK of a particle in a gas. So yeah, that's pretty much the entire off-topic B.3. Once again, I'd like to reiterate that this is possibly the easiest way to get marks in IB physics. So if you can get really good at this topic, then that's great news for the exam. I hope this helped you, and thank you so much for watching.